This is the Tacoma Narrows Bridge in Tacoma, Washington. It opened on July 1st, 1940. Only 4 months into its life, on November 7th, 1940, the bridge experienced operating conditions that were not accounted for by the design. It took only 45 minutes of operation in this condition to collapse the bridge. And there was one fatality, a beloved Cocker Spaniel named Tubby. What do the Tacoma Narrows Bridge and every mixed-use, mission-critical data center in the world have in common? The bridge in its day and data centers today do not take advantage of modeling and simulation to properly account for operating conditions. This oversight put the bridge on a path to disaster. Data centers are following the same exact path. Data center failures are not as visually spectacular as a bridge collapse, but they are a catastrophe in their own right for the operator. Due in part to the Tacoma Narrows Bridge collapse, the United States federal government now requires that all bridges built with federal funds must utilize modeling and simulation techniques to account for a wide range of operating conditions. Sadly, there is no similar standard or requirement for data centers. Welcome to the virtual facility, a sustainable approach to data center operations without compromise. This presentation is about the need for modeling and simulation standards for the data center. It's obvious why bridges need to be modeled, but why do data centers need to be modeled and simulated? The computer game Tetris is a good way to illustrate this. Tetris is challenging because the player has no control over the blocks. They change shape randomly as they appear. Every placement requires a good decision to avoid wasting space on the board. There are no rules of thumb or guidelines that can prevent the space from being wasted. This is the Tetris effect. Data center operations is challenging for the same reason. The operator has no control over the characteristics of the IT units. These are controlled by IT manufacturers. Every deployment requires a good decision to avoid wasting space, power, and cooling resources. Just like in Tetris, there are no rules of thumb or guidelines that can prevent the Tetris effect from occurring on data center resources. Can you see the Tetris effect on space and power in these two cabinets? But wait, IT equipment requires cooling also. Can you see the Tetris effect on cooling? No? You can't see it? That's right, because cooling is invisible. It's done by airflow, which cannot be seen or measured in the data center. This highlights a major challenge for the operator. You can see the impact of unexpected operating conditions on the Tacoma Narrows Bridge. You can see it in the computer game Tetris, but the Tetris effect in the data center is invisible. So how can the operator manage a problem that can't be seen or measured? This brings us back to modeling and simulation. This is an actual facility. This is a computer representation of it called the virtual facility. Visually, they look very similar. Behaviorally, they're almost identical. In this sense, the virtual facility is a digital replica of the physical data center that accurately mimics its behavior. This is extremely powerful and greatly improves decision making because the operator can quantify the Tetris effect of proposed changes beforehand. But before we dive into this further, let's shift gears and talk about the cost of the Tetris effect. For mission-critical facilities, the Tetris effect will destroy 30% or more of the intended data center capacity. Total cost of IT capacity can range from $10 to $20 million per megawatt of IT load. Losing 30% can amount to a $3 to $6 million per megawatt of IT load in capex losses. Depending on energy rates and the type of cooling system, the Tetris effect will drive up cooling costs by 30 to 40% and increase PUE by 15%. This can amount to an extra $250,000 per year per megawatt of IT load on the energy bill. But these costs pale in comparison to losing IT services. At about mid-life, the Tetris effect typically has spread throughout the data center enough to expose IT equipment to failure conditions for the first time. This is a very difficult position to recover from. This is the point where the operator leaves capacity on the table and invests in new data center space or expands into a colo space. It should be noted that these numbers apply to mixed-use, mission-critical operations where the data center is meant to be a flexible IT platform. They don't apply to purpose-built data centers such as those from cloud or hyperscale computing companies like Google and Facebook. Every change to the data center produces a Tetris effect to a greater or lesser extent. There are three common scenarios where the Tetris effect is overlooked. The first is when IT, facilities, and operations, or another group, makes decisions for the data center to advance their cause, but in the process undermines the data center as a whole. This happens often without these groups even being aware of the impact of their actions. So here's an example. The facilities team wants to reduce energy costs by replacing the old AC blowers with new EC fans. This decision seems like a no-brainer because EC fans deliver the same amount of air for 30% less power. Meanwhile, after installation, energy was saved, but temperature compliance for 30% of the installed units was lost. Facilities got what they wanted, but IT services were taken down in the process due to an unseen Tetris effect on airflow. Project planning, like a server installation, is the second scenario where the Tetris effect is overlooked. Today's state-of-the-art practices are based on DSIM tools, but DSIM is real-time information only, such as power consumption, temperature, and alarms, like what you would see on a car dashboard. This information describes what is happening now in the data center, but reveals nothing about the hazards on the roadmap ahead. Just like driving a car, the data center needs headlights to reveal the hazards in its path and enable the operator to steer clear of them. Let me give some examples of the need for data center headlights. Here's an example. IT is planning to install these units into this cabinet. DSIM tools would not distinguish one stacking order from another. In reality, the Tetris effect on cooling is dramatically affected by stacking order. An overheat will occur with the blade computer on the bottom. Blind application of DSIM is like traveling the data center roadmap without headlights. Now, these animations were produced by the virtual facility. They provide a preview of the Tetris effect, which enables the operator to select a path that minimizes it. Here's another example. IT is planning to install these cabinets into this data center. They can choose one of two roadmaps. Again, DSIM tools would not distinguish between the two roadmaps. But in reality, the Tetris effect on cooling is dramatically affected by the roadmap taken. An overheat will occur if roadmap A is selected. The preview of the Tetris effect from the virtual facility ensures the operator selects roadmap B. Capacity planning is the third scenario where the Tetris effect is overlooked. Today's state-of-the-art capacity planning practices are based on DSIM tools. But again, DSIM provides real-time information only, like a car dashboard. This information is incomplete and cannot be used on its own to replan the roadmap when changes occur. The data center also needs a GPS to ensure that it can reach its destination before running out of capacity. Let me give an example of a data center GPS in action. IT is planning to change the data center roadmap with a new IT technology. Two roadmaps are being considered. DSIM tools would not distinguish between the two. There is enough space and power no matter where the IT configuration is located. But 5 years down the road, roadmap B will have temperature compliance problems. This will stop the data center build-out before reaching its destination. Only roadmap A has a chance at reaching a fully loaded, fully compliant final state. Once again, only the virtual facility can provide this information to the operator before selecting a roadmap. Okay, now it's time to summarize. Today's decision-making practices for the data center are flawed at best. They are plagued by the Tetris effect. That isn't supposed to happen. But operators allow this to happen when they make decisions within a silo to optimize a part of the data center. And this approach tends to pessimize the data center as a whole. We saw an example of facilities trying to reduce energy consumption only to unknowingly compromise IT services. The Tetris effect will happen also when decisions are made without a view of the roadmap ahead. Every change produces a Tetris effect to a greater or lesser extent. Planning changes using DSIM information only conceals the Tetris effect until the problems are severe enough to set off alarms or cause failures. As a computer model of the data center, the virtual facility overcomes these shortcomings with the ability to mimic the behavior of the real data center. It works like headlights and a GPS by revealing the Tetris effect anywhere along the route to a fully loaded, fully compliant data center. The industry is starting to become aware of the need for modeling and simulation, but there's a long road ahead before this technique becomes an industry standard. Dr. John Koomey is one of the few industry researchers who understands the need for modeling and simulating the data center. He has written 2 papers on the topic that can be downloaded from the Future Facilities website or John's website at koomey.com. Thank you for your time. We hope you found the presentation interesting and informative. Please email us at info@futurefacilities.com for more information. We look forward to seeing you at future presentations, and thank you again.